This is the fourth chapter in the video pamphlet on agonist deficiency. In the first chapter, we defined deficiency in terms of the weak and strong binding energies. The second chapter, we described some patterns of agonist deficiency in skeletal muscle nicotinic receptors. The third chapter, we described the origins of deficiency as an energy linkage between catch and hold. These are events inside of binding and inside of gating. And in this chapter, we're going to talk some of the implications of the catch and hold mechanism with regard to the rest of the gating isomerization. The subtitle of this pamphlet is Reflections on the Motive Power of Agonists, which is a takeoff on the famous 1824 pamphlet of Sadie Carnot, which was called the Reflections on the Motive Power of Fire. Carnot was trying to understand how heat could drive steam engines. William Thomson, also known as Lord Kelvin, was a big fan of that pamphlet and named these reflections thermodynamics, fire and motive. So in honor and homage to William Thomson, perhaps the field of understanding how ligands activate proteins could be called chemodynamics. And the first three chapters of this pamphlet have focused on the chemo part of that, on changes in agonist energy. And now we're going to switch our attention to away from the agonist and to the rest of the protein and try to understand the dynamics of the gating isomerization using what we've learned about efficiency as a starting point. This is where we left off in Chapter 3. We had divided binding and gating into sub-events. Binding involves the diffusion of the ligand to the binding site and then a local rearrangement of the binding site to establish the low-affinity complex. Gating involves a number of protein motions, one of which is called hold, and that's another local rearrangement of the binding site that switches the affinity between low and high, between weak and strong binding. And we mentioned there are sub-events in the rest of the isomerization as detected by phi-value analysis and directly by flip and prime. So we're going to now focus our attention on these sub-events, which are here indicated by asterisks. And in particular, we're going to focus only on the sub-events that take place inside the gating isomerization and try to reveal the nature of not the states, but the events that separate the two states, the intermediate states. And just as catch and hold, we suggested were linked by a linear free energy relationship and a zipper mechanism in which the one of these processes promotes the subsequent process by lowering the transition state, an idea stole from enzymology. We're going to see if we can continue to steal that idea and use it to go through the rest of the isomerization. Just to make things clearer, in our first three chapters, we talked about agonist efficiency, which is the ratio of those two blue lines, depends on the ratio of those two blue lines, which represent the energy, the weak and strong binding energies to the binding site. That difference in energy is the efficacy, but the ratio of those two energies determines agonist efficiency, and that we use the Greek letter eta to symbolize efficiency. And in words, efficiency was the fraction of binding energy converted into gating energy. So it's the chemo motive energy link. Now we're going to switch away from the binding site, and we are going to study another energy ratio, and that is the ratio of the change in the energy at the transition state relative to the change in energy of the open state. And that ratio is called phi or phi. And the ratio of the change in the transition state is proportional to the log of the opening rate constant, and the ratio of the change in the open state is proportional to the log of the gating equilibrium constant. This is L2 with two ligands, and in words, phi is the fraction to which the residue energy at the transition state is like that at O. In order to study phi, what we do now is we make a mutation of a side chain and measure the change in the opening rate constant and the change in the gating equilibrium constant and plot those in log-log format. And that's going to be the focus of Chapter 4, is the ratio of these two blue lines to the right. Here, once again, is the thermodynamic cycle shown in the form of energy landscapes or potential energy surface of the receptor conformation, left without agonists and right with agonists. And you recall that the uphill reaction going from C to O turns into a downhill reaction because the binding energy to O of the agonist is much stronger than it is to C. That's the length of this line is longer than this line here. And you will also recall that the agonist had the same affinity or nearly the same affinity as O at the transition state as it does in the open state. So that means that the barrier separating C from O is much smaller when there's agonist presence than without, and that means agonists open the channels rapidly. They lead to a increase in the opening rate constant. So the focus of this chapter 4 is going to be on this barrier region, because we're interested in how the protein gets from C to O, and that happens inside the barrier, where it's on the left side of the barrier at C and the right side of the barrier is O, so the changes are taking place in the barrier. The good news is this is a very interesting part that we can get at through an analysis called phi value analysis, which I will describe in detail, and we will be able to understand what's happening inside of the isomerization, albeit indirectly. The bad news is these events are very short-lived. This is a region of instability, and it's very difficult to get a direct measurement and have a direct view of what's going on in there. Certainly there are no clear structures yet of what's going on in nicotinic acetylcholine receptors here. Most of the structural investigations focus on the stable states, C and O. And these unstable states are very transient, on the order of hundreds of nanoseconds, so it's very difficult to study. But I'm going to show you a way that we can get at break down what's happening in here and understand the motive, the motions that are taking place inside the protein. As I did with the first 3 chapters, I'm going to start by showing an unexpected experimental result. And that is, if we measure those 2 bars that determine, those 2 energies that determine phi, and we do this for many different residues. In this case, this histogram shows it for 137 residues, that we see that phi is distributed as 5 discrete populations. It's surprising because no one really had made such measurements before, and it wasn't known that there would be any distribution whatsoever. I think most people would have expected phi values all across the map, or maybe all at 1 and 0 and nothing in between. But this is what we got after a lot of work, and I'm just going to show you quickly the names of the people that did the work. This was a huge labor that took nearly 20 years and nearly 20 people to work on, and probably more than 20 papers. So I'll go through the people in more detail in the acknowledgments, but I just wanted you to know that this is a huge amount of data that's going to be summarized in the next few slides. The picture at the top is of a neuronal nicotinic receptor binding site, showing the agonist in pink, in this case nicotine, surrounded by a cluster of aromatic amino acids. So the agonist is, in a way, like a side chain. It's about the same size as a side chain. It's not one of the 20 natural amino acids in nicotinic receptors, although it is in other receptors. But the acetylcholine is roughly the same size as a side chain. It's different from amino acids because, of course, it's not covalently linked, and therefore it is free to come and go and serve as a signaling molecule. And it's also different from other side chains because the wild-type neurotransmitter, namely acetylcholine, is much more stable in the open state, stabilizes open much more than it does closed. And that's not the case for most amino acids. When you mutate most amino acids, what you do is you lose the stability that the wild type is given to C. So that uphill reaction is there because most side chains are most stable or happier when they're in the C conformation or energetically more stable. And when you make a mutation, you lose that stability, and therefore you sort of increase the unliganded gating equilibrium constant. It's not 100%, but that's generally true. But that's not true of agonists. The wild-type agonist is acetylcholine, and that has the largest stabilization we've measured so far of O relative to C. The bottom panel shows a phi plot, or a linear free energy plot, between the log, a reefer it's sometimes called because it's a rate equilibrium free energy plot. On the y-axis is the log of the opening rate constant, which is proportional to the energy of the transition state. And on the x-axis is the log of the gating equilibrium constant, which is proportional to the energy of the O state, the diliganded O state. And in both cases, we're assuming that the C state is zero. That's the anchor point for the energy diagram. So you can see that when we change the agonist here, which is, I'm making an analogy to changing a side chain, you see that we get a reduction in both for all these agonists, we get a reduction in both the opening rate constant and the gating equilibrium constant. But the point is the reductions, the relationship between those two, the ratio of those two lines stays constant. And that ratio was 0.93 in this paper, in this plot. We've done this for many more agonists. They all fall on a slope of about 0.93 to almost 1, depending on who's doing the experiments. So it's a high phi value for the agonist. And I want to just point out that water is on this plot, which means that water is the dividing line between what's an agonist and what's an inverse agonist. Everything shown here to the right of water is an agonist. And if there were inverse agonists, and we have yet to find any of the nicotinic acetylcholine receptor, it would be to the left of this line. So water is the dividing line between what's an agonist and what's an antagonist, but it does fall on the plot nonetheless. Now, what about those aromatics around there? Well, we have made mutations of not only these 5 aromatics, but several other residues in the vicinity of the binding site. And they all also turn out to have a high phi value. So here's an example of mutations of this tryptophan 149, which is a highly conserved and a very important residue. And you see when we plot the opening rate constant versus the gating equilibrium constant, the points fall on the slopes on a straight line. So in this plot, each point, each symbol is a different mutation. I think we made 18 or 19 different mutations of tryptophan 149 and measured its effect on the opening rate constant and the equilibrium constant. Now, in this plot, there was no agonist present, so we were just interested in what the effect of the was on L0. We measured L0, not L2. So if you remember the green equation from the first chapter, the gating equilibrium constant with 2 ligands is the product of the gating equilibrium constant without any ligands. That's L0 times the coupling constant, which is the ratio of equilibrium dissociation constants. So we removed the equilibrium dissociation constant from this, and we're just measuring the unliganded gating equilibrium constant. And as I'll tell you, that I think that this is going to be true for most of the measurements that we make. So in any case, the slope of this one was 0.88. Some of the other ones are higher. They're also in the range of that purple, in the population of purple that was shown in the histogram of 5 values. So we're going to call everything at the binding site is purple in the range of which has a mean value of 0.95. That means at the binding site, the length of the transition state energy change is approximately equal to the length of the open state energy change. And we're going to give that name hold. That we named that hold, that's when the inside of gating, when the affinity switches from weak to strong. So we repeated this process over and over and over again for many different residues throughout the protein, away from the binding site. Here is just a sampling of residues away from the binding site that were published, that were shown in this paper shown down at the bottom, where you can just add my name in Buffalo and you'll get a unique hit in your database. So each panel in this plot is a different residue, different amino acid, and each point in the panel, let's say here, let's take this as an example, is a different mutation, different side chain at that. One of these is wild type, but the rest of them are mutants. So we measure at the single channel level, we measure the opening rate constant and the gating equilibrium constant for each of these mutants. These are the averages of 3 patches each. And we fit these measured values, we plot them on a log-log plot and fit these to a straight line, and the slope of that straight line is phi, which is the ratio of those two blue arrows I showed in the previous energy landscape diagram. So this is a plot of log plot of opening rate constant versus gating equilibrium constant. And you can see we did this for 137 residues. This is, I don't know how many is shown in here. And each residue required a significant number of mutants, let's say 5 to 10 mutants per residue. So in that histogram that I showed of phi, there's really roughly 1,000 or more different mutations, all analyzed at the single channel level. What this slide shows is that the mutations that were shown in the previous slide almost certainly do not change the coupling constant or are far away from the binding site, but what they do change is L0, the unliganded gating equilibrium constant. So even though we're measuring these in the presence of ligand, we're measuring L2. The change in L2 is caused only by a parallel change in L0, not by a change in the coupling constant. So we're measuring changes in L0 throughout this histogram. So that's shown here in this experiment where we measure the change in L0 relative to some background, and we measure the change in L2 using choline as an agonist, a weak agonist. So we see the change in L2 and the change in L0. When we plot these versus each other, we get straight lines with a slope of 1. Which means the change in L0 and the change in L2 were the same. There was no change in the coupling constant. So the open circles are for the fetal type receptor, which has a gamma subunit between the 2 alphas, and the solid symbols are for the epsilon adult type receptor, which has an epsilon between the 2 alpha subunits. And you can see that the slope of 1 indicates that the change in L2 was caused exclusively by a change in L0. And I will discuss this plot. I'm planning to make a subsequent video on L0, and this was one method that we used to measure the wild type L0. But that's not the topic of this chapter. Here we're going to be concerned about this histogram, which is those slopes. Each entry in this histogram is a slope from one residue, and we see 5 populations which are 95%, 79%, 58%, 33%, and 6%, like where the transition state has that energy character relative to the open state. So what does phi mean? What information does phi provide? Well, the first thing it provides is a sequence of events. So in this simulation, we have decided to make gating a linear chain of sub events. That in this case there is 1, 2, 3, 4, 5, 6 sub events. So there are 5 intermediate states in this simulation, and later on we'll reduce this to 4 intermediate states. But this example shows what we did in the simulation. We perturbed in this one. The solid line is the wild type, and we perturbed the second in that linear chain, the second step in that linear chain. We either make it more favorable, energetically more stable, just that event. The rest of the events stayed the same, or we made it less stable, and again the rest of the events stayed the same. So at the end of the day, that change in the second event either increased or decreased the gating equilibrium constant, and we could measure the rate constant change by that perturbation. And you can, as you might expect, if you perturb something early, you're going to get a change in the rate constant. But if you perturb something that happens at the end of the chain, you're going to get a very little change in the rate constant, even though the change in the equilibrium constant is going to remain the same. And that's shown here in the main body of the plot, where the black points correspond to the simulation shown up above when you perturb the second in the chain. And you can see we get a straight line in our reefer, and that straight line shown in the lower inset has the phi value, has a slope of about 0.8. And we do this simulations again for the first, second, third, fourth, and fifth, and each one of these gives you a reefer, and we measure the slope of the reefer, and as you perturb later and later in the reaction chain, you get a lower and lower phi value, meaning you have less and less an effect on the opening rate constant, even though the equilibrium constant effect stays the same. So that set of experiments, which was later supported by some analytical results, where we could solve this mathematics of phi in a linear reaction chain, indicates that these 5 populations indicate that there are 5 rearrangements taking place inside of gating, and these rearrangements are separating 4 intermediate states. So phi gives a sequence with a phi value of 1 meaning early and a phi value of 0 meaning late. So that's our first inference from phi, is that it's telling you that there are 5 rearrangements that occur in sequence inside of the gating isomerization. The second thing phi gives you is the energy landscape of the barrier region. Again, that's shown in these, given in these 2 papers in 2005, 2017, shown below. Now, in order to solve the barrier region, we have to assume that the intermediate states are all very brief. So we have no information about the lifetime of these states. But we do have information about the ratio of rates out of each of these intermediate states, and that gives you the roof of the barrier region, the shape of the roof of the barrier region. So this is actually calculated from the phi values shown at the left. We calculate the shape of the transition state region. Of course, these are very short-lived, and therefore this just looks like a smooth potential energy surface in our low-power telescope. This is not the James Webb telescope. This is the old Galileo telescope we're using here. So, but we are able to get a shape of the binding site, and we are able to identify where the committer is, the transition state. That's what this double dagger indicates. And the committer is the point that you can think of it as if you've dropped the ball at this point in the landscape, you would very quickly end up in C or in O with equal probabilities. So that's the energetic separator between C and O. It's called the committer, and that's what we have identified here from the phi values. So the phi values calculate the landscape, calculate where the transition state is. And I've shown you the 1, 2, 3, 4, 5 transitions. Now, I want to emphasize that we are focusing on the barriers, the little local rearrangements, not the intermediate states that separate the barriers. Structural biologists who are interested in what these states look like, we are interested in the processes that separate the states. So we can draw this as a reaction scheme shown below with a parameter called K, which is gives you the depths of the wells, and we don't know what that is, but if we assume that they're all the same depth, that these barriers are all the same, we end up with K equal to about 300,000 per second. So you can look at that rate constants if you're interested in those. But again, but what we can do is we can again turn to simulations and take our model derived from the phi values and simulate currents, and we can see that we predict that there are 1, 2, 3, 4 very brief intermediate shut states inside the closed histogram, the shut histogram, at infinite bandwidth. We pick the 300,000 per second because that predicts a component at about 5 or 6 microseconds, which is what has been measured experimentally as flip or prime. So that's we use the flip and prime data to give us a time scale, because phi does not provide time information, it just provides energy information. But you can see that the closed channel histogram is consistent with experimental data, which roughly has a time limit of about 10 to the minus 5 seconds here. So if you just imagine this histogram a cut in this histogram at about 10 to the minus 5 seconds, you would just see the rising phase of this, and you would say there's only one component of 6 microseconds. These other components are completely missing from the experimental data. So if we turn back to our sequence of events, now we can put a time scale on these of approximately 500 nanoseconds. Although we don't know much about this, there could be quite a bit of variation between these, and we don't know the lifetime of these states. Someday we hope these states will be seen in some cryo-EM structure and identified as such. But right now, there's no real structural information about these intermediate states. So the affinity change occurs at the beginning of the sequence. That's hold. There are passage through 4 intermediate states and a transition state that sits somewhere between at the end of the third and the fourth transition inside the gating isomerization. All this we learned from phi, the map of phi, from the distribution of phi. The third thing we learned from phi is location. So on the right side here is shown a plot of about 80 different mutant cycle analyses. And in mutant cycle analyses, you mutate residue A and measure the change in the gating equilibrium constant. And you mutate residue B and measure the change in the gating equilibrium constant. And then you make the pair mutations and you measure the gating equilibrium constant. You compare the pair to the sum of the individual mutations. And that's what's shown in the y-axis as the interaction energy, which is the deviation of the sum from the pair. So if there's no deviation, for example, it would be a zero interaction energy. And we plot these interaction energies as a function of the distance. Now, there's noise in both of these axes. Of course, there's noise in the measurement, and this orange bar represents what we think is the noise of our measurement, which is about 1.6 kcals per mole, or 2 kT approximately. And on the y-axis, there's noise because first we're using C-alpha distances, not residue centroids distances. And we're using also GluCl as a template structure to measure distance, because at that time we did these experiments, the nicotinic skeletal muscle nicotinic receptor was not known. Structure was not known. So you can see from this plot that mostly there is very little interaction energy. I think this is that's 1 kT. Yeah, 1 kT is what these dashed lines are. So mostly we're in the thermal noise for the interaction energy. But there are a few residues that are significantly interacting. And most of these, however, are in short range separation. This line is drawn at about 18 angstroms, and when you're more than 18 angstroms away, there's only a few interacting residues. There are a few of these. I'll mention these a little bit in the next plot, but I'm not going to go into them in this chapter here. But the point of this is that when you make a phi measurement, you're measuring the change in the energy of the residue locally. The energy is not moving through the protein. It is a local deposition of energy, exchange of energy with the environment. So that allows us, that feature that phi is reporting a local energy chain, allows us to make a map of phi values. So again, using GluCL as a template, this is a color code of phi values with each residue colored according to its phi value. This upper line here represents the level of the binding site, and this line here represents the interface between the extracellular and transmembrane domains. And in this plot to the left, the white balls means residues that we studied. We made mutations and we measured the rates and equilibrium constants, but the spread of values along the equilibrium constant axis was too small to allow a slope to be measured, which means these guys don't change much between C and O. The white balls are mostly superficial, and they don't change much between C and O. It's the color balls not only give you the phi value, but they tell you that there is a significant change between C and O. And on the right, we've exploded this according to phi values, showing the purple balls, which are 0.95, are mostly at the binding sites. And there are a few at the extracellular transmembrane domain interface, and these could be quite interesting, but I'm not going to go into these now. We don't really understand these. We have to take into account the fact that these are mainly loss of function mutations and therefore could shift phi according to something called the Hammond effect, which I won't get into here. But so to a first approximation, the purple balls are clustered around the binding site. The blue balls, which represent the phi values of 0.78, are in the extracellular domain. There are none in the transmembrane domain. The green balls are all in the transmembrane domain. There are none in the extracellular domain. And the red balls are mostly around the gate region in the equator of the transmembrane domain, but there are some spread across, and I'll mention what that spread might be due to. I want to say that this plot, this plot is just of the alpha subunit values that we've just repeated on all 5 subunits. So this is a plot of the phi map of alpha subunit. So we did look in some regions of the protein at all 4 subunits, and that's shown here. This is the pore lining M2 helix. M2 lines the pore with the gate region being or between the 13 and 9 prime regions at the equator of this pore. And you can, I'm not going to go into this, there's a lot of information in this, but I just want to point out that the brown residues, which are the phi near zero residues, are all sort of below the equator at or they're below the gate region in non-alpha subunits, although the 9 prime of the alpha subunit is also brown. It moves late in the sequence. And you can see the alpha subunit moves earlier than the epsilon subunit, which moves earlier than the beta and delta subunits. So let's put this together and put the sequence and the map together and describe the conformational cascade or gating conformational wave. So here's the histogram of phi values that gave us this sequence of events, And now we can localize these to different regions of the protein. And in related receptors, these regions have been shown to change structure in specific ways. So I not only will name the first event hold, the one that switches the affinity of the binding site from weak to strong, but the extracellular domain motion I'm going to call twist, because there is a twisting motion of the ECD compared to the rest of the protein. There's also a compaction, or an unblooming as it's called, but I'll use the word twist to describe that conformational change. I'll use the word tilt to describe the rearrangement of all the transmembrane helices, not just M2, all of them. The word rip I'm going to use for the motion, the gating motion of the gate region between the 9 and 13 prime, and I'm going to define pop as the fusion of the two water compartments, the extracellular and intracellular water compartments, which is what allows ions to start crossing the membrane. And I'll also include part of pop. There's going to be some motion of the membrane. So these hold, twist, tilt, rip, and pop are the names of the 5 sequential conformational changes that separate these 4 intermediate states, which together form something, the flip or prime event. The infinity change is associated with hold, and the conductance change is associated with pop. So let's put these in motion just with a little animation to emphasize the sequential nature of the gating conformational change. So first, hold, twist, tilt, rip, and I'm not showing pop because that's taking place in there, at the M2 region. I just want to briefly show in the next slide the interface between the extracellular domain and the transmembrane domain, which represents the interface between phi blocks. So I'll call each of these a phi block or a phi group, and I just want to emphasize it's a fairly discrete transition from going from the twist motion to the tilt motion, from the phi of 0.8 to the phi of 0.6. There's a structurally discrete boundary between those. And I'm going to show this boundary at a pi helix in the M1 helix of the alpha subunit. So on the left this is the binding site here, and these are the 2 beta strands, beta strand 9 and 10. There's a linker between the extracellular domain and the transmembrane domain. And the first transmembrane helix here is highlighted in blue, and the arrow indicates the reason I'm showing in the slide to the right. There is a conserved proline in this M1 helix, which changes the hydrogen bond backbone of the protein and causes the formation of a pi helix in this region between 217 and 221. Is pi. And if we measure phi values, you can see here on the left that the extracellular domain is blue and the transmembrane domain is green, mainly 0.8 and 0.6. And this brown area represents the gate region in the background. So here we've measured all of these residues, phi values for all of them. And here is the phi map, the reefer for N217, which gives a slope of 0.84, both with and without agonists. Mutations of this residue don't change KD, as we reported previously in a mistaken paper. To correct that mistake, I want to emphasize these do not change KD. The mutations here are changing only L0. But they give a phi of 0.84, which makes them blue in the blue domain. And this residue here, 218, which is its neighbor, has a phi value of 0.59. So there's a very sharp break. I just want to point out in phi 218, there's a gigantic sensitivity to mutations in terms of the gating equilibrium constant. This is 6 orders of magnitude in terms of from Y to A at V218. Later on, I'll mention this residue Y again. But you see that has a residue, has a phi value of 0.59, and the proline, which is what breaks the hydrogen bonding, is also a phi of green phi of 0.62. So it's unremarkable. The proline itself is unremarkable with regard to phi. So, but it does cause the pi helix. So this pi helix is very important. It represents a very discrete boundary between phi blocks. Now, I'll also point out that there are two red residues up above in the blue domain here. This is normally an all blue domain, but in this linker there are two red residues, meaning a low phi of 0.3. And I don't think that these represent the motion of the protein here. I think both of these residues are in contact with the lipid, if you look at structures. And my hypothesis is that there is a very late motion of the lipid that follows the fusion of the water compartments, and that these residues get bumped twice in gating. So they get bumped once at the blue line. This is R209, which is a very conserved residue, but is not essential for gating. You can make mutations here, and gating works fine. But we think that these residues that are red are bumped along with the blue, and then they get a second perturbation late in the game, which lowers their phi values. And there are several complications of phi, and that's one of them, that there could be multiple jostles going on. And the second one is there is curvature in the phi plots, both Hammond and anti-Hammond effects. So I'm not going to get into that here, but just to say that there are complications. So in the final section of this chapter, I'm going to zip up the ACHR, use that zipper mechanism that I invoked for the mechanism that coupled catch with hold. So that zipper mechanism is that linear free energy relationship is shown by this symbol, this paperclip symbol, showing that catch here in orange and hold are linked by a linear free energy relationship, where catch promotes hold by lowering the transition state. And that is what I call the zipper mechanism. And we have shown, or we have proposed, that hold, twist, tilt, rip, and pop are sequential subevents inside of the rest of the gating isomerization, with the transition state being located somewhere in the tilt rearrangement, and that these asterisks represent the intermediate states that someday we hope we will find structures for. Right now we have C and we have AO, but we don't even have AC, which is this state right here, which is the closed ligand state. It can be considered an intermediate state in this process. And just to remind you, so what we're going to do is we're going to link all these by the paperclip, by the same linear free energy process that we use for catch and hold. So catch promotes hold, promotes twist, promotes tilt, promotes rip, promotes pop. They're all going to be linked in a big, long linear free energy relationship to connect C, unliganded C, with liganded O, the activation of the receptor. And just to remind you, that the blue line here highlights the states that all have high affinity. Everything after hold is a high affinity state. So I've given these names now with primes, AC prime, AC double prime, triple prime, and quadruple prime, that I think together these four states represent flip, are also called flip. But this is the AC state, which everyone puts in there, even though it hasn't been found structurally. That's the low affinity state. And of course, there's a very low affinity state here before the agonist has formed the low affinity complex. And the black line represents all the states that are non-conducting or shut, all the way from C. In this model, the only states that is conducting is O. And this shows the linear free energy relationship between those states. So this is the model that we have shown up above, where catch and hold and everybody else is linked by a linear free energy relationship. And I want to say that this is not just wild speculation or just derived by analogy to catch and hold, that the linkage, the linear free energy linkage throughout the isomerization, I think that this can be used to explain an unexpected experimental result shown, I think, in Chapter 3, which is shown here below, which is that the association rate constant of agonist to O is not only faster than to C, but is roughly at the diffusion limit and the same for many agonists. So here, ACH, carbachol, and TMA all have approximately the same association rate constant, which is near the diffusion limit, which is this dashed line here, 4 times 10 to the ninth. Choline is slower. But these three agonists are roughly at the diffusion limit, and they are all significantly faster than to C. Notice that this is a log scale here. So this is 10 to the 10th, and choline is 10 to the 6th. So the question is, why are these agonists that all have different, very different affinities, both low and high affinities, all have the same on rate constant when the channel is O, but very different on rate constants when they're to C. You recall that we use this reduction in C with a reduction in EC50 to divide binding into diffusion and catch. So now we want to try to use this model shown above to try to explain why these guys are at the diffusion limit. And the idea is shown in this thermodynamic cycle to the right, which is this line at the bottom is the catch conformational change, and this line, this purple line here, is the hold conformational change. And we have, in Chapter 3, we show that the catch event lowers the transition state for the hold event so that hold can take place. So that hold very rarely takes place without catch happening. That's given by this dashed line. So the difference between the thickness of the lines here, the thickness of the lines represents the equilibrium constant for the process. So the fact that you have a very thin line with it before catch and a reasonably thick line after catch means that catch promotes hold. That's what this arrow means. Now, in a thermodynamic cycle, there is something called microscopic reversibility, which means that the getting to an endpoint is the same regardless, the energy is the same regardless of the path. So if this path is very small, then this path must be very large to close the cycle. So that catch, so that means if you find yourself having undergone hold, rarely it will happen. If it happens first, you're very rapidly going to also catch. So the microscopic reversibility means that if catch promotes hold, then hold promotes catch. And this must happen also throughout the rest of the isomerization. So hold and twist, twist and tilt, tilt and rip, rip and pop all promote each other. So what this means is that if I make a mutation that makes the channel open constitutively, which is how we made these measurements here on the left, we added a mutation, the channel was open constitutively, and we added a little bit more agonists, and we were able to detect the actual binding event to the open state and get the rate constants into and out of the open binding site. If you make a mutation that does that, and here I'm using the mutation V218Y, that was the extreme mutation of that M1 pi helix residue after the pi helix, or inside the pi helix. And if we make a mutation here that makes that happen with great probability and therefore increases open probability, what that mutation is going to do is going to not only promote the subsequent events in the chain, it's going to promote the preceding events in the chain. So you're going to get up and down. It's going to be bidirectional is what's going to happen. You're going to get all the way through to catch, because catch promotes hold. So in this case, tilt promotes twist, promotes hold, promotes catch. So that's why when you make these mutations that cause constitutive activity, you are also promoting catch all the way across. So you cross. This is where everything to the right here is called, to the right of this point is called gating, and everything to the left is called binding. But the linear free energy actually links those two. So you cross the binding gating divide and enforce catch when you make mutation that causes constitutive activity. So microscopic reversibility ensures that catch accompanies catch is accompanied by catch accompanies constitutive activity. So finally, let's put this together and show you how I imagine the energy landscape for gating changes when you add an agonist. The inset here shows what you recorded in our patch clamp. The patch clamp is great as long as you're not interested in things that are faster than a microsecond. And as we're interested in 100 nanoseconds events, so these things sort of blur together into these energy barriers that we draw. But in fact, they're corrugated with lots of bumps inside. And that's what I've expanded out here, is tried to show what the bumps are. Now, this is not done quantitatively according to Phi, but this is just the idea. And the idea I'm going to put together is that the gating isomerization acts as a zipper. And I'll show this twice. First, let's focus in on the energy landscapes. The agonist arrives. It lowers the energy. Sequentially lowers the transition state of the next event, allowing it to occur. And this blue energy landscape turns into this black energy landscape, and that's shown here in these inserts at low bandwidth resolution. So you go through, after diffusion, you have catch, hold, twist, tilt, rip, and pop. And now I want to show this again in structure. Let's focus in on the structural part, because we do have phi gives you the location. Our phi map allows us to locate these in the protein. So that's the ion shown up above, and you can see the binding site with the ligand inside. And now we're going to go through catch, hold, twist, tilt, and pop. And then the ions can go through. So that's my imagination on the energy landscape changes in ACH receptor gating, and it's done through a zipper mechanism wherein each preceding conformational change in the sequence promotes the subsequent conformational change by lowering its transition state. So the idea being that the structure of the intermediate, which has one domain has become active, must match the transition state for the subsequent conformational change. So that's the end of the pamphlet on agonist efficiency. We did a definition. We defined efficiency. We described some patterns. We proposed a linear free energy relationship between catch and hold, between binding and gating. And we extended this linear free energy relationship throughout the gating isomerization. And I think this might be a good way to move energy across distance only by local conformational change. So each of these phi blocks is within our 18 angstrom distance for energy transfer inside the protein. So you move 1, 2, 3, 4, 5 of these things in a row, and that's the way you move energy over distance, only using local conformational changes. So I hope you will stay tuned for the acknowledgement sections which follows.